The potential of solar power for generating nearly emission-free and sustainable energy has been known and used for decades. But with the rise of anthropogenically influenced climate change and nuclear catastrophes like Fukushima, some states, like Germany, have decided to alter their energy supply plans from conservative to alternative or green energy technologies. This has pushed the renewable energy economies and research a lot. Most of us are used to the sight of solar fields and single plants on private rooftops, but especially big institutions like the University of Heidelberg have enormous energy consumption due to numerous laboratories and huge scientific machines like particle accelerators or medical technologies. In 2012, the university had an energy consumption of 43 gigawatt-hours and spent 6.5 million euros on electricity. The share of alternative energies in the whole mix amounts to at least 35%. Some of this is generated by solar plants that have been installed on the rooftop of the Institute of Chemistry. With the highest energy consumption between 11 AM and 3 PM, solar plants can help stem the need at the university in the most critical hours of the day.
Also wir haben hier auf der Uni zwei Anlagen installiert. Das ist einmal die Anlage hier und einmal bei Sport noch eine. Und das war
We installed two plants at the university in 2011, the one you can see here and another one at the Institute of Sports. This is a photovoltaic system, which is also indicated by the blue color of the silicon. Those are modules from Canadian Solar, and the plants are like tubs, which are simply placed on the roof, but not anchored. When sunlight falls on the panels, the photovoltaic effect is induced, which initiates a flow of electrons that is collected from the single modules. This direct current is then collected from all the modules and led to the inverter. Here it is converted to alternating current, which is also what we get from our sockets at home. Afterwards, it's fed to the Institute's power supply system. For this plant, which reaches a peak of 72 kilowatt-hours, we had to pay about 150,000 euro. We can assume that we have a solar radiation of about 1000 kilowatt per square meter in Heidelberg over 1 year. That means that you get about 1000 kilowatt-hours per year. So on balance, this plant produces about 70,000 kilowatt-hours a year.
Das heißt, man kann ungefähr davon ausgehen, 70.000 Kilowattstunden produziert die Anlage hier auf dem Dach.
The performance of such plants could be increased with better planning and calculation of factors such as shadows. Recently, scientists strive to fulfill those tasks by developing new methods to calculate the course of the sun and its dependent shadow to maximize the efficiency of solar plants. Some of these scientists are from the Department of Geography at Heidelberg University. They use modern technologies like laser scanning, also called LiDAR, short for light detection and ranging, to produce highly detailed 3D models of the environment. Laser scanners work by sending out pulses of infrared laser light. Whenever the light hits the surface, a portion of it is reflected to the scanner, which calculates the distance to the object and produces a point cloud with millions of coordinates that merge to a 3D model of the scanned area. With those models, various analyses can be processed, for example simulations of shadows cast by nearby trees that could temporarily cover solar plants and diminish their performance.
Ja, im Vorfeld und bei der Planung haben wir uns natürlich viele Gedanken darum gemacht, wo ist der beste Standort für die Anlage.
With the planning of this plant, we did a lot of thinking about the optimal location for the panel. A lot of different factors play a role for this process. Firstly, it is the condition of the roof itself. Some have superstructures and some need to be reconstructed prior to installing the solar plant. We can settle these questions by looking at aerial images or inspecting the roofs. Often we find additional negative influences, like the trees to the south at the roof right here, which force us to cautiously take care of shadowing effects within the detailed planning. This means we have to balance the size of the plant considering economic sense, because shadowing reduces the performance of the panels. There are methods to calculate the influence of shadows which can help us with the weighting. This is very important because reduced power output is directly falling back to us as plant operators. We have to ensure the economic efficiency is guaranteed over the service life of the plant. As you can imagine, it would be a great problem for us if we placed the panels in the shadow. This is why we thought a lot about shadowing effects in the first place. Here, laser scanning could have been an additional improvement, since common shadowing analysis methods mostly don't consider the third dimension of objects. So with those trees, for example, it is almost impossible to recreate the permeability for sunlight without 3D models. There is commercial software for these purposes, but we used a self-programmed tool to calculate the shadowing influences. But I guess most of them reach their limits when it comes to dealing with vegetation, especially since its permeability is depending on the season.
Auf jeden Fall wichtig, da sehr detaillierte Aussagen auch zu machen.
Together with students, the Heidelberg Geographers developed a tool to calculate the path of the sun throughout the day and the year, based on a C++ algorithm. As input, it uses common vector files and a digital elevation model of the study area. With this 2.5D information, they can create a 3D model of a line segment and calculate the solar radiation on its surface. This can then be used in common GIS software to determine optimal areas and orientation angles to maximize solar panel performance. Those algorithms can also be used in laser scanning point clouds to compute the path of a shadow, like in this example. Throughout one day, the individual shadows have been calculated in a 3D model of a tree. This approach could be applied for numerous studies that depend on the course of the sun and the shadows cast. The method could, for instance, be used to simulate the influence of the surrounding trees on the rooftop at the University of Heidelberg. Among others, one study that relies on this approach is the idea to utilize highway noise barriers for solar panels. As these objects are already widely present, the idea of using them for this purpose seems natural, but not every segment of those barriers is suitable for solar panels. Sometimes, nearby objects cast shadows, or the orientation of the walls towards the sun is not ideal. With point clouds, those negative effects can be calculated precisely, even if there is no barrier yet. The potential solar output can then be integrated in common GIS software and used for further analyses. One disadvantage of this approach so far is the little availability of 3D point clouds. So it is still not possible to make extensive calculations for large regions without previous collection of data. But the applicability of such tools goes even beyond the mere calculation of optimal places for solar panels. A new approach tries to improve the predictability of hedonic real estate pricing models based on solar income. Normally, the value of a property depends on factors like location, living space or furnishing, and the hedonic approach tries to predict this value based on previous sales. Here, laser scanning has been used to calculate the amount of sunlight a flat receives throughout the day, depending on nearby shadowing buildings or vegetation. For the first time, this can be computed for the third dimension, and is thus more reliable, since the amount of solar income depends highly on the height above the ground. The amount of sunlight in turn determines running costs and increases quality of living. Consequently, owners of sun-drenched flats should be willing to pay more for their property. As those analyses can be produced for each flat separately, this method provides a significant improvement of hedonic real estate pricing models.